Hi, my name is Shahaf. I will be talking about hardness versus very little structure in cryptography from the perspective of multi-prover interactive proofs, and this is a joint work with my advisor Gil Segev. So let's get started. The starting point of our work is the striking difference between the current state of private key primitives, such as hash functions and block ciphers on one hand, and public key primitives such as public key encryption and oblivious transfer on the other hand. First, private key primitives have many candidates, while public key primitives have very few candidates. Also, the security of private key primitives is often based on the hardness of problems which seem to not have much structure, while public key primitives are based on problems with a strong structure. A consequence of this situation is that for many private key candidates, our current attacks are believed to be nearly the best, and this is crucial for choosing concrete security parameters. For public key primitives, we have considerably less confidence that our current attacks are the best possible, and current candidates are endangered by algorithmic advances, with either classical or quantum computers. For more details on the connection between public key candidates and structure, we highly recommend Boaz Barak's blog post, which we mention in our paper. This difference between private key and public key primitives raises the question of whether structure is necessary for public key cryptography. To move further with our discussion, we need to define more carefully what structure means in our context. Or, when should a computational problem be considered structured? While there's no clear-cut answer, we consider the following popular choice. Since one-way functions already imply the existence of hard languages in NP, a problem is structured if it is contained in a complexity class that is not believed to contain NP, such as NP intersect CONP or statistical zero-knowledge. Intuitively, the fact that a problem belongs to such a class is due to its exploitable structure. And this is exemplified here by several hardness assumptions and primitives that imply hardness in these classes. So we can restate our question and ask whether public key cryptography implies the hardness of a language in any such class. First, for one-way functions, already in 88, Rudish showed that they do not imply the existence of any hard problem in NP intersect CONP in a black box way. More recently, Bitansky, Degwekar, and Vaikuntanathan showed that even injective one-way functions, together with indistinguishability obfuscation, or IO for short, do not imply hard problems in NP intersect CONP in a black box way. They also showed that they do not imply hard problems in statistical zero-knowledge in a black box way. These primitives do imply public key encryption, oblivious transfer, and even functional encryption in a black box way. So as a result, all these primitives do not imply hard problems in NP intersect CONP or SZK in a black box way. At this point, one may wonder, isn't obfuscation inherently non-black box, since it directly deals with circuits? The short answer is that by considering Oracle-aided circuits, which are circuits that contain gates that issue calls to oracles, it is possible to model natural obfuscation-based constructions as black box constructions. However, we won't get into these details in this talk. It is important to mention that both the results of BDV and ours, which I will describe in a moment, hold even if IO does not exist. That is, the primitives on the left-hand side still do not imply the existence of hard problems in the classes on the right-hand side in a black box manner. Now, in our work, we showed that injective one-way functions, together with I/O, do not imply hardness in the class AM intersect co-AM. I will define the class AM later on, but note that AM intersect co-AM contains both NP intersect co-NP and SZK, so we generalize the two results of BDV. However, the result of BDV for SZK holds also for promise problems, while ours holds only for languages. Our result is even more general, and we show that injective one-way functions, together with I/O, do not imply hardness in the class MIP intersect co-MIP in a black box way, where MIP is the class of languages with multi-prover interactive proofs, which I will define later on. However, this seems contradictory, because NP is contained in this class, and already one-way functions are known to imply hardness in NP in a black box way. To understand better the meaning of our result and how this is in fact possible, we need to explain the definitions of MIP and black box constructions. So, in a multi-prover interactive proof system, we have a polynomial time verifier and two non-communicating computationally unbounded provers. The verifier is given an input x and may use randomness r while communicating with the provers. Then the verifier outputs a bit, and we say that this is a proof system for a language L if for every x in L there exist provers that make V output 1 with probability at least 2/3, and for every x not in L, no provers can make V output 1 with probability greater than 1/3. The class IP is the restricted case where only one prover is allowed, and AM is the further restricted case where only a constant number of communication rounds is allowed. One can also consider more than two provers, but it turns out to be polynomially equivalent to two provers. Now, since we want to capture a black box use of cryptographic primitives, we consider Oracle-aided proofs where the verifier can use a primitive psi using Oracle queries. And now the corresponding language can depend on the specific Oracle. More formally, for the MIP co-MIP case, the definition is as follows. We say that a pair V bar of Oracle-aided polynomial time algorithms defines an MIP co-MIP protocol pair relative to an Oracle psi if there exists a language L psi such that for every x in L psi there exist provers that convince V with probability at least 2/3, and no provers convince V bar with probability greater than 1/3, and for every x not in L psi, no provers convince V with probability greater than 1/3, but there exist provers that convince V bar with probability at least 2/3. This finally allows us to define black box MIP co-MIP. So a fully black box construction of an MIP co-MIP protocol pair of a worst case hard language from a primitive G is a triplet V bar, and M of Oracle-aided polynomial time algorithms such that for every instance psi of G, the pair V bar defines an MIP co-MIP protocol pair relative to psi, and for every instance psi of G, given access to an oracle that decides L psi, M breaks the security of psi. This means that if psi is a secure instance, then it is hard to decide L psi. For example, if we consider G to be an injective one-way function, then the correctness should apply to all injective functions, and by breaking the security we mean inverting the function on a uniformly random input with a noticeable probability. Now we can state our result more formally. Our main theorem is that there is no fully black box construction of an MIP-CoMIP protocol pair of a worst-case hard language from an injective one-way function f and an indistinguishability obfuscator for f-aided circuits. As I said before, I won't define what this I/O means exactly, but rather in this talk we will focus on injective one-way functions. And this already covers a significant amount of our technical contribution. Now we can formally understand what previously seemed to be a contradiction. There is a black box construction of an NP verifier V for a hard language LF from a one-way function f, and since NP is contained in MIP intersect CoMIP, the language LF also has an MIP CoMIP protocol pair. But this pair, and in particular the CoMIP verifier, cannot be obtained from the NP verifier in a black box way. As a side note, this is related to the fact that the containment of NP in CoIP does not relativize, but black box constructions do relativize. This leads us to the conclusion that if a complexity class A contains a class B, it doesn't necessarily mean that a black box construction of a hard language in B implies a black box construction of a hard language in A. Moreover, the same complexity class can have inequivalent definitions of a black box construction. For example, since IP equals IP intersect CoIP, we can define a black box construction of a hard language in IP from a primitive G in two ways: an Oracle-aided interactive proof for the language, or a pair of Oracle-aided interactive proofs for both the language and its complement. For any primitive G, a black box construction of an IP-CoIP pair trivially implies a black box construction of an interactive proof. But a black box construction of an interactive proof does not necessarily imply a black box construction of an IP-CoIP pair, as demonstrated when G is a one-way function. We note, however, that the issue of inequivalent definitions and the issue that containment does not imply black box constructions appear only in higher classes, namely IP and above, where non-black box techniques are used to establish some of the containments between complexity classes. These issues are typically not present in lower classes, such as AM intersect CoAM, where most, if not all, containments are established via black box techniques. For the rest of the talk, I will sketch some of the main ideas underlying our proof and conclude with some remarks. As already mentioned, I will focus on ruling out constructions based on injective one-way functions. One general paradigm for ruling out a black box construction of a primitive B from a primitive A is to show a distribution O over oracles relative to which there exists a hard instance of A, but every instance of B that is based on the above hard instance of A is efficiently solvable. Note that there is no need to show that there are no hard instances of B at all, but only that there are no hard instances that are based solely on A. In our case, we need to show a distribution relative to which there exists an injective function that is hard to invert on a uniformly random input with a noticeable probability, but the language defined by every MIP-CoMIP protocol pair based on this injective one-way function is efficiently decidable. Our oracle is inspired by the BDV oracle used for ruling out a black box construction of a hard NP-CoNP language. So let's first describe their oracle. It consists of two components, an ensemble of injective functions f and an additional oracle to which we refer as NP-decide. F is an ensemble of uniformly sampled injective functions, and the NP-decide of f is defined as follows. Given oracle-aided circuits C0 and C1 as input, NP-decide performs the following computation. For every ensemble G of injective functions, it checks if one of the following cases holds. Case 0 is when C0 outputs 1 on some input Y0 relative to the oracle G, and C1 does not output 1 on any input Y1 relative to the oracle G. Case 1 is similar to case 0, but with the roles of C0 and C1 switched. Now if there exists any G for which none of the cases holds, then NP-decide of f outputs the bottom symbol. Otherwise, it outputs 0 or 1 according to whether case 0 holds or case 1 holds for f. So this was the BDV oracle, and for our oracle, we replace NP-decide of f with the following MIP-decide of f. Given oracle-aided interactive circuits C0 and C1 as input, MIP-decide of f performs the following computation. For every ensemble G of injective functions, it checks if one of the following cases holds. Case 0 is when there exist provers that convince C0 to output 1 with probability at least 2/3, and no provers convince C1 to output 1 with probability larger than 1/3. Case 1 is similar to case 0, again with the roles of C0 and C1 switched. As before, if there exists any G for which none of the cases holds, then MIP-decide of f outputs the bottom symbol. And otherwise, it outputs 0 or 1 according to whether case 0 holds or case 1 holds for f. In their proof, BDV made the following observation about their NP-decide oracle. Let f be an ensemble of injective functions, and let C0 and C1 be oracle-aided circuits that contain at most Q oracle gates. Then, there exists a small set C of critical queries, where by small we mean that its size is at most Q, and by critical we mean that for every ensemble G of injective functions that agrees with f on the queries in C, the answer of NP-decide on input C0, C1 relative to f and relative to G is the same. This is proved by letting C be the set of all oracle queries issued in any single accepting computation for either C0 or C1 according to which case holds for f. However, when switching to our MIP-decide oracle, there is no such single accepting computation, but rather acceptance is determined by possibly exponentially many computations. Therefore, in our work, we make the following more refined observation that still allows us to prove our result. Let f be an ensemble of injective functions, and let C0 and C1 be oracle-aided interactive circuits that issue at most Q oracle queries during their execution. Then, there exists a small set I of influential queries, where by small we mean that its size is at most 3Q, and by influential we mean that if we modify f on a single input that is outside of the set I, then the output of MIP_decide on input C0, C1 does not change. As for notation, we denote by f sub x maps to y the ensemble obtained by modifying f to output y on input x. Note that modifying f on more than a single input, even outside of I, does not guarantee that the output of MIP_decide does not change, as opposed to the critical set of BDV. This is proved by letting I be the set of all heavy queries of either C0 or C1, according to which case holds for f, when interacting with any specific pair of convincing provers. By heavy queries, we mean queries that are issued in at least 1/3 out of the possibly exponentially many executions. As we will see now, this observation is useful enough for showing that f is one-way. But for our fully fledged result that includes I/O, we further extend this observation and introduce additional IDs. These IDs are not included in this talk and can be found in our paper. So let's indeed prove that f is one-way. Our proof follows the path of the proof of BDV, but we use our observation instead. We consider the following hybrid experiments. The first hybrid is the real one-wayness experiment, in which we sample x, give the adversary f of x as input, and answer its queries using our oracle. Because f is injective, the adversary wins if its output x prime is equal to x. In the second hybrid, we sample y outside the image of f and answer its queries using a modified oracle, where we modify f to output y on input x and modify MIP_decide accordingly. The views of the adversary in the first and second hybrids are identically distributed, where in the second hybrid we just renamed f of x to y. In the third hybrid, we again sample y outside the image of f, but now we answer the queries of the adversary using the original oracle. It is clear that the view of the adversary in this hybrid is completely independent of x, and therefore the adversary wins with probability at most 2 to the minus n. It remains to show that the views of the adversary in the second and third hybrids are indistinguishable. Note that the adversary's view in the third hybrid differs from its view in the second hybrid only if one of the following events occurs in the third hybrid. Either A queries f on x, so this query is answered differently, but since the view of A is independent of x in this hybrid, this event occurs only with a negligible probability. The other option is that a query to MIP_decide was answered differently. But this occurs only if x belongs to the influential queries corresponding to this query to MIP_decide and f. And again, since the view of A is independent of x in this hybrid, and since the set of influential queries is small, this event occurs only with a negligible probability. So the views of the adversary in the second and third hybrids are indeed indistinguishable. As a result, the probability that A output x in the real experiment is negligible. To conclude, here's again our main theorem with the corollary to public key cryptography. It further extends the result of BDV and shows that public key cryptography does not imply even little structure in a black box way. So we shouldn't lose hope in basing public key cryptography on unstructured problems. So that's it, and thank you for listening.